Here's our warm-up for our lesson. This is on the notes I handed out, and this is important. We're going to use this to start our lesson, but it's going to be built into the next things we do. So here's what we have. We have a theoretical cannon. It's a safe cannon, okay? And it is shooting starting from 10 feet off the ground, right? So this theoretical cannon is shot 10 feet off the ground at an acceleration of 406 feet per second. And it is in theoretical Angry Bird space, okay? And there's no gravity pulling on it. Okay, so we're starting with the theoretical. The cannon shoots, it goes straight up, 406 feet per second. There's no gravity pulling on it. I want you to use the table to map out what would happen and then write a function for the situation. All right, do I have a volunteer to help me with the table?
Yes.
All right, Raymer, what am I doing over and over?
You're just adding 400.
Okay, so 1 second, where am I?
416.
Yep.
822.
Yep.
1228.
Okay.
1634.
Okay.
2040.
And so I'm starting at 10 and going up by 406 each second. Is that what you're telling me? So the equation, the distance is always going to be, we're at 10, and we're increasing our speed by 406 each second because there's no gravity in this theoretical cannon world, okay? Everybody good with that? Repeated addition is what? Which makes the slope of a linear function, right? Slope of a linear. This is a linear. This number is called our y-intercept. It's our starting value, right? The y-intercept, here's a fun word for you, and this will be coming up. The y-intercept's called the constant. Because does it ever change? It's just 10. It's just 10. Always 10, constant. This is changing depending on the time. Okay, so now we're going to go next step. This is the next thing in your notes, Bob. The next step, you're going to look at the data for a real cannonball with gravity. As soon as that cannonball leaves the cannon, what's another force pulling on it? Gravity. Right away, right? So you're going to compare values of your two tables. That's in your notes that I handed out. And then you're going to graph them, and you are going to try to write the function for the gravity cannon. And it is derived from what you know about gravity already. We did it in our warm-up in class, right? You know something about gravity and a function, and you know something about how linear the acceleration is. There's going to be those two things come together. So try 3 will tighten up together if it isn't right, but you're going to work on comparing them two different ways, the data sets. You're going to graph them, and then try to make a function of the one with gravity. Okay, so as you guys pointed out, this isn't increasing by as much. And I'm not going to draw the perfect graph. Well, it's pretty. Did you guys notice the scale made it kind of tough?
Yeah.
At 1, 4, 16.
Yeah, absolutely.
2, 1200-ish.
Around
Or 2, 800-ish. 3, 1200-ish. 4, 1600-ish. 5, 2000-ish. And so it's not perfect, but it is linear, right? The 406 each second. Wait. I messed that up. I just graphed. Oh, no, that's right. Whew. So that's the line, the linear one. The other one starts really similar, but what do you notice about the outputs?
They're so different. Holy crap.
They're,
That's like way down.
these ones are all coming out being smaller, right? 3, 4, is that like 1300 instead? And what do we notice about the gap between the two? It's getting bigger because this one is going to look more, it's going to flatten out. It's going to go as high as it can go, then what's going to happen? It's going to come down because now we have gravity. So let's look at the function of this new one. So the function of the new one, we already kind of talked about it, right? Where is it starting? 10. How fast is it coming out the cannon? 406 T. But now we have this new force exerted, minus 16 T squared. That gravity's pulling it down. I think it's beautiful that you can see what's happening in the function. It's like cool. Like if you didn't have context, this would just be a quadratic function, right? Like it'd just be letters and numbers. Context and that being the same thing, I just think it's awesome. So what you're going to do next is the reverse. We're going to do the Desmos stuff together. I'll get that going. So you're going to just do number 1. You're going to say what each of the terms means in context. This is not on your notes handout. You can write it on the blank bottom or do it in your math notebook. Up to you. So again, we're going to do the Desmos together. Who can tell me what the fitty means in context? Emmett.
It's the y-intercept and what it starts at.
So y-intercept, where it's shot from. And we're going to start using some fancy language. It's called the constant. It doesn't change. It's always fitty. Always starts at fitty. Everybody good? Yeah. Okay, I'm going to erase that. There's not a lot of room on here. Okay, who can tell me what the 312T means in context? Tiff. Slope, okay, that's true. In context, in terms of like the cannonball, what is it? How far away in seconds? Yeah, so I'm going to use the word acceleration. But that's exactly what you said, that many feet per second. So is this one faster or slower than the last one? So the last one was 406 feet per second, okay? And then this other third part, the negative 16t squared, what does that tell us? Eliana?
It's like the amount of gravity pulling down on the...
Yeah, it's gravity pulling it down. And I think, again, the coolest part is I can see all these things on the parabola. I can see all these things happening, like if I imagine a cannonball being shot. It's up on a hill, 50 feet up in the air. Comes out that cannon, 312 feet per second, and gravity's pulling on it until it comes down and hits the ground, right? Isn't it kind of cool how you can just see it? The function is the context is the function. That's math. Not just a collection of numbers and letters, right? It's a way to use and explain things that are happening. That's my, and when you realize that about math gets way cooler, right? So you guys notice it doesn't look good, right? So we need to go change our axis. I'm going to go 0 and 20 for the x-axis. So we're changing our domain. Let's see.
How about your range?
0 and 20 looks good. Yeah, I can't see the top. So I'm going to try, the notes say 0 and 2,000.
That sounds like a good range to me.
Nice.
And there we go with the
I can see the parabola now. So in context, here's what's happening. It starts at 50 feet. How high does it go?
2,000.
1,571. How long does it take to get there?
900 seconds and 7.5.
Okay, let's see when it hits the ground. 19.659. So if we're talking domain and range, do we need any times other than 0 to 19.659? Does it make sense to go like before it shot out of the cannon for any reason? Nope. Does it make sense like after it hit the ground to keep, to know something way down here? No. Maybe just after if it went in the ground a tiny bit, maybe we could do that. And then what about the range? We could maybe go a tiny bit below ground if we think that cannonball is not going to stay on the top. For a range, would we need to go higher than the highest point? No, that's the maximum value, so we wouldn't need to go higher. That point has a special name. It's called the vertex. And this point right here also has a special name. It's called a 0. What's 0 there? X or Y?
X.
What? Y. X is 19.659 seconds, right? So that is the solution to the quadratic, and that's where we're going to be moving in the next few lessons too, is getting solutions, using places on the parabola to make some inferences, okay? There's a 0 right here too, but does it make sense to go negative time in context? In context doesn't make sense for the domain. So this one, the function has 2 zeros, but in context, we would just have this 1 0, which would be the solution. Cool. We're going to go back to our slide presentation. We just handled all this stuff. There's that 0 function where it hits the x-axis. And you are going to practice these things on your lesson summary. You're going to show me your lesson summary to get the homework today.